Okay, back here for a video talking about definite integral and area. And area does have a relationship with the definite integral. So other than just mentioning that the definite integral is going to be a tool that we use to find area beneath a curve or a function, bound by some region of X and Y. And, we'll take a look at an example here. For instance, the equation of a circle with the radius of 2, or at least the top half, is f of x equals the square root of 4 minus x squared. So that would be function going all the way from here over to here. But this particular example, which I believe is in your textbook, um, actually is just dealing with the restricted domain of going from 0 to 2. In other words, we're just ignoring the rest of this, or the left part of this graph here. And if we just use our basic formula for area, we can find the exact area of a circle using the formula of pi times the radius squared. So if I take pi times the radius, which is 2 squared, I am going to get 4 pi. But because we're dealing with a fourth of the circle here, then I'm going to multiply the area of the entire circle by 1/4, and that just ends up with pi. So what we're going to essentially do with calculus here is we start by approximating the area with rectangles that are, circumscribed or inscribed, different ways of looking at it. These happen to be circumscribed, which is, again, they're going to overestimate the area. And then we're going to use inscribed ones where we are going to underestimate it. And then we actually can use a midpoint. So let me explain that further. Okay. So let's just suppose here we have two subintervals. So we're going to break up the interval from 0 to 2 into two equal subintervals. Okay. 0 to 1 and 0 to 2. And so we're going to call that our delta x, or our change in x. It's just a unit of 1. And essentially what we're doing is just using the function to determine the height of the rectangle. So if I take f of 0, that gets me to this point on the graph, which is 2. All right. So I'm going to take the width, which is 1, times the height of the rectangle, which is f of 0. And then to get the area of this rectangle, again, I'm going to take the width times the height. And so that's going to be 1 times f of 1 is going to determine the height here. All right. So all I do is I take the area of the left rectangle, add the area of the right rectangle, with a little bit of, mathematics and substitution. We skipped all the details. We get 2 plus the square root of 3, or about 3.7 units, okay, or square units for the area. Now, if I use inscribed rectangles, that is rectangles determined by, this case, the right endpoint, they're inside, then I'm going to let f of 1 be the area of the first rectangle. I know it's kind of weird, but f of 2, which is the height of 0, is going to be the height of the second rectangle. So I take the height of the first rectangle, which is 1, or I'm sorry, f of 1 times the width, and I take f of 2 times the width. Well, this is going to give me the square root of 3 here for f of 1 times 1, and then f of 2 is 0, as we said over here. So I just end up with the square root of 3. So notice the true area is pi, which is about 3.14. Obviously, this is going to overestimate it. This underestimates it. So if I try to balance that out and go in the middle, I'll let the middle of the interval determine the height. So here's my width, 1, and here's the height, which is f of 1/2. That's halfway between 0 and 1. And then f of 3/2 is 1.5, or halfway in between. I take and add those area of those two rectangles together. Notice how much closer I am. And obviously, because again, I'm adding this extra area, that's why I overestimated. Here, I'm losing all this area, this little bit right here, as well as this. Here, I kind of overestimate by this much, but underestimate. And they're kind of canceling one another out, so to speak. Okay, here's, again, an underestimation. That's a little white area here, and here's a overestimation. So they're kind of balancing each other out and end up with about 3.3, okay, which is a lot closer to 3.14 than either of these two. So what's I guess the whole point? Well, the whole point is this. Let's say if I have break up now to four intervals, okay, subintervals. So I'm going to go 0 to 1/2, uh, 1/2 to 1, 1 to 1 1/2, and then 1 1 1/2 to 2. And notice that's all I'm doing here. I'm just letting those values determine the height of the rectangle. So now, even though I'm overestimating like I did before, because it's almost like, more rectangles fit better underneath this curve. And even though I'm over it on every one, notice I'm not too far away from 3.14 like I was in the other instance over there on the previous slide. And then if I would even do that further, add a few more in here. Notice I have 1, 2, 3, 4, 5, 6, 7, 8. So I'm going every 0.25 or every quarter unit. Notice I keep getting closer and closer to that 3.14. All right. And that's the idea. I can have smaller and smaller intervals and I can keep adding those, let's say maybe I go from 0 or make them be 1/8, then 1/16, then 1/32, then 1/64. Well, again, knowing mathematics, there's no end to that particular pattern. And that's essentially what we're going to say is that we're going to take the number of rectangles, let's just say n, and add all those up, all right? And then take the limit as n approaches infinity. In other words, take the limit as n approaches infinitely many rectangles, okay? That doesn't mean they're going to equal, it's approaching infinity. So they're going to get closer and closer and closer, or skinnier and skinnier and skinnier. So, this delta x for my first example was 1. You remember, that was the width of the rectangle. It was 1. That's a delta x, or change in x. Here, my delta x was 1/2. For this example, my delta x was 1/4. And again, there's no end to how small I can go, right? I can go to 1/1,000,000. I could go to 1/10,000,000,000. All right. And again, I'm going to get some area there. And so the idea is that that area, okay, as I get n rectangles, you just tell me how many rectangles you want. That's what n will be. Then I consider the limit is the number of those rectangles approaching infinity. That is going to be the exact area. Okay. And we actually define that to be a definite integral. Now, if you look at the notation here, this thing looks a lot like the indefinite integral, except now we have these two little numbers here. So you can maybe anticipate if, we already worked problems without the a and b and knowing that we just found antiderivatives. So we know that we are going to get antiderivatives playing in here, okay, based on what we had just done. And, this idea of a sum, that's kind of what this notation, this looks a little bit like an S, okay, and that's where the integral sign, I mean, we call it an integral sign, but there's a relationship between that and the Greek letter sigma. I just wanted to show you, well, the type of problems you may get here are pretty simple, and I just use this view as an example, but they may give you, a function like, this is a pretty simple one, a line 4x plus 3, and then they're going to give you the subinterval. So the delta x is 3, right? So if I go from 0 to 3, 3 to 6, 3 to 9, that's my delta x. So even though I have 4 numbers for endpoints, I still have 3 subintervals or 3 rectangles I'm adding up here. And all they want you to do is evaluate that. So, it's just more or less a matter of being organized. So using the formula here, since I have n is 4, I have 4 rectangles. I'm sorry, 3 rectangles, but I have 4 endpoints. I am going to take f of the first endpoint. So this would be a left sum. So I'm going to let the left endpoint be the height of the rectangle. So all I need to do is take the height times the width plus the height of the next one times the width plus the height of the next one times the width. Okay. And there I have it. Okay. As far as the area of these 4 sub intervals. Okay. So now all I need to do is go ahead and add up all those areas. And so I'm going to go ahead and do that. I add up my first interval right here. Okay, take the height times the width, height times the width, height times the width, and height times the width. So I get one rectangle, the area is 9. The other rectangle, the area is 45. The other rectangle, 81, and then 117. And I just add all those up, and I get 256. Okay. So that's pretty much, straightforward here. We have 4 values that we're using here. Okay. And, again, we're starting in 0 here. They gave us the sum from we're adding up 4 areas. Okay. So they gave us the area. I mean, they literally just, if I wrote this out, okay, if I wrote this out, and I would start at 0 for the height of that rectangle here. This would be like using, um, 4 rectangles to estimate that area. Okay, so I don't know what else to say. This is just, just a plug, substitute in and simplify type problem here. But I want you to understand what we're doing here in terms of evaluating that. So we could look at these as approximations, right? Because we're not considering the limit right now. We're just adding up those values here, those areas of those rectangles, and that's approximating this definite integral. And we'll talk about how we find the exact value here in a moment. Okay, so we'll leave this video at that, and we'll be back with the next one.